This narration film is about some hard to understand topics in the slides. Some of your friends have given me feedback about the problems of their understanding in the slide information in the slides. So this movie is to help the people who have some difficulty in comprehending the slides. For example, in week number 7, slide 23, 24, 25, the figures are without explanation. So it's a little bit hard to understand, so let's analyze them. It's about data transfer to the memory and from the memory. The figure is 8-16 from your textbook. A, which is this one, is byte transfer by the 8088. So there is a transfer of byte information. So this is a memory map. Okay, so this a piece of memory map. So this rectangle is say 5 address locations in the memory, and it's selected by address pins A0 to A19. So this is a 20-bit line. We transfer information X, which is a byte information, by using the data bus. So this is like a memory, data bus, address bus, and control circuitry or pins are not shown to the address. So there's a byte transfer. In part B of this figure, okay, so this X plus 1 is kind of misleading. So we only transfer byte. This is 8-bit information, which is X is written to shaded address location. Okay. In part B of this figure, same microprocessor, this time it transfers a word. Word is 2 bytes, which means 16 bits. So memory has 8-bit locations. So the first address is selected by address pins. Data is transferred at location X only. So first byte is transferred to the first location. The next byte in the second bus cycle is transferred to the next location. So which is 16 bits. So 8-bit part is transferred to X. The other 8-bit part is transferred to the next address. Low byte to the low address, high byte to the high address, which is, as you know, little endian conversion. So this figure represents byte or word transfer in 8-bit microprocessors. Slide 23. Slide 24 is again transferring some information. So let's try to analyze the figure. We do have this time 2 chips. Okay, so the data bus is here, okay, and which is data 0 to data 7 and data 8 to data 15 bits, okay, and similar figure, okay, conditions hold for B as well, data bus, okay. So this is the first cycle, this is the second cycle. In the first cycle, the first 8 bits In the next cycle, next 8 bits. So there's a 16-bit transfer here. Okay, this is for 16 bits microprocessor, which is 8086, sorry. Okay, so it's transferred again in 2 cycles with 2 different bus schemes with 2 different portions of the data bus by using bus control signals. Okay, or it can be transferred simultaneously. At the same time, 16-bit transfer occurs to the same address in the microprocessor. So there's another kind of convention. This can be considered as double word, which is 32 bytes. So x plus 1, x plus 3. So 4 addresses which each consists of 8 bits. So this should be bits equals to 32 bits. Okay. So there's a kind of order. First this, then this one. So shaded ones are the active ones. Data bus active. So we transfer x plus 1 to this location, then x plus 2 to this location, and we can repeat for x plus 3 as well. So it's the storage of 32 bits to 4 consecutive addresses. Next topic, which is hard to understand, is from week 7, slide number 27. What is this? This is a timing diagram, bus cycle and time states. Well, that's a little bit compact form. Okay, the first one is clock. As you know, that's a symmetrical 50% duty cycle square wave with highs and lows. Each 4 cycle is a machine cycle, and in the first moment, address type of activities are done in fetch and decode cycles. Okay, address latch enable starts to store the address information to the corresponding latches. There are 3 latches, you remember, in 8088 and 8086 processors. These enables these latches for address type of activity, address control and address data. This is for multiplexed pins. Each pin may be address or data depending on the condition. So it's controlled by other control pins like this. So the others are later. Okay, so address 0 to address 15. So this is a 16-bit thing. 16 bits are multiplexed, and the other 5 addresses are or can be sent directly. So this is the first moment for address information. So the reason for address selection is either memory or input output. So if it's a memory, then it's 1 for memory selection. If it's I/O, it's 0 for I/O. So this is the compact figure for 2 options. You can have 2 stable thing, either memory or I/O. So 2 curves, actually it's like this. For memory, for I/O, there are 2 curves here. They are combined here. And then in the next half cycle, either read or write operation can be performed. So this combination is for reading and its control, associated control. with this, and the other two combinations for write. So again, what do you want to do? Reading something from I/O, then I/O should be low, read signal, and the others. If you want to write something to memory, memory should be high, and read should be always high. There shouldn't be any active low portion. Write should be activated at this time. So the first one shown here is a read procedure, because we have read operation, no write operation. The second one here is a write operation. We have active low write signal, the read signal is high. Okay, so this figure carries everything in a compact form: reading, writing, memory, input, output, address, writing or selection, and real activity. Again, address select, latch enable, addressing, and then writing. So let's come to the next difficult point. Week number 8, slide number 53. This is an example of address decoding. It says a circuit containing 32 kilobyte of RAM is to be interfaced with an 8-bit microprocessor, which is 8088, so that the first address of the RAM is 48 or 48000 hex. Okay, starting address is 4800 hex. What's the entire range of RAM address? How is the address bus used to enable RAMs? What address lines should be used? 32 kilobytes means I have 2 to the 5 times 2 to the 10 locations. So this is kilo, this is 32. So we need 15 address pins to address. So let's check in the solution. Do we have 15? Okay, so 15 address lines or pins are used for addressing RAM. So it's given in here. These 15 address lines will select one location inside the RAM. Okay, so the solution is given and consistent with our estimation or calculation. The rest should be used for selection. Whenever the address is 4, which is 0100, and 8, 100. The first address of the RAM is all zeros, which is this. The last of the address is 4 and all ones. Okay. So this is the base address. What's the entire range in the RAM address from this address to that address? There are 32 kilobytes or 68 locations. How is the address bus to use enabled RAMs? What address lines should be used? So these 5 address lines should be used. In order to select it, we can design an address decoding circuitry. So this is 17. And whenever this is 0, this is 1, this is 0, this is 0, and this is 1, my output is low. And we have to use at least 5 input NAND gate. There is no 5 input NAND gate in the market, so we can use 13 input NAND gate with 8 other inputs are connected to high, for example, which does not change a thing in the logic. So this is a simple control logic circuit for this problem. I hope this is more understandable right now. Week number 9, slides 6 and 7 are also created some confusion. These diagrams are a bit simpler than previous timing diagrams. So let's analyze these as well. This is input bus cycle of 8-bit microprocessor. So one machine cycle has 4 clock cycles, clock periods, and 5, 16, 17, 18, 19, 4 pins are either address or control pins. So there are 4 timing diagrams on top of each other here. And from A15 to A8, 8 address pins are directly taken out from the microprocessor. They are not multiplexed. 8 pins are multiplexed with address and data. There's a multiplexing here with address and control. Okay, so A15 to A8 are not multiplexed address lines. And we start by setting the address. First, address latch enable. So the information at the address lines, so this is all information in the address lines are latched. Then input output memory set to high for I/O. If it were 0, then it's memory. So it's a read cycle. Then other controls, data transmit, read, enable, etc. can be activated. So this is a read sequence input. So information in the bus is read to the microprocessor. So this is output. Output means from the microprocessor, which is 8-bit, to the bus. From the microprocessor, that's a write operation. So write is taken to low. The others are the same. Address latch enable. First address, then writing and other controls. So this is from the microprocessor towards the bus. So this is data bus. Another point in the confusion is week number 9, 45, 46 number slides. The slides are about some operational principles of parallel printer ports. Well, they were very popular in the past, but they are not used anymore. This is a cable used for parallel port interface. Okay, this cable does have 2 outputs. Okay, one cable connector, which is called a D-type connector, goes to the computer. It's a 25-pin D connector. And the other connector is connected to the printer with parallel port. But these printers do not exist now. The printers nowadays are using USB connection. So these are obsolete instrumentation. There are some controls, signals, names, etc. are explained. We have not covered in the classroom. We may skip. And these are data pins, strobe, acknowledge, busy are signals in that printer port. Again, they do have some kind of convention of active, high, low, data, etc. And there's a kind of data should be ready before I mean, it should be settled before some deadlines, so there's a transfer, etc. So this diagram explains parallel port timing. But since we are not using parallel port devices very frequently, they can be omitted from your items in the course. Other slides of confusion are given in 64th and 69th slides of week number 9. 64th slide is an application. There's a microprocessor over here, 8088 or 8086, and it's connected to 8255 programmable input-output integrated circuit. You may have 3 ports, which can be, all bits can be programmed or as input or output. So this is the final topic of your lecture. So PA0 to PA7 are port A0 to 7. Shortly, port A pins. You connect port A and you connect 2 bits of port C and port C6 and port C7. Okay, those are port C, one of the other ports. And port C0 to port C5 pins are not used, and neither of port B pins are not used. So port A has the row contents, port C has the column contents. Whenever you press a push button, then what do is you connect a logic level of high, okay, this resistor, and this line is always high. You can draw this line to low, and if this detects high, then that means this key press is released. Or pressing this key whenever this is high sends A to here. Okay, once again, this is the output, 2 arrows, so you can send low signal or high signal, and there when you don't send the signal, this is high, since it's connected to plus 5 volts by resistors. So if you send high, doesn't matter. If you send low to here and check this signal is low or high, if it's high, then this key is not pressed. You observe this signal, but there's low signal in the column. Okay. When no keys are pressed, all receive high information. So the hexadecimal information is FF. If any key is pressed here, then associated bit at that pin would be low, so you receive another information, so you can detect which key is pressed when you send low and high from here. So if you oscillate lows and high and check this key, you can follow which key is pressed in this scheme. So there are 16 keys here, so this is like hexadecimal keypad. So this key check is the flowchart of the software. First, you read input port. This is the input port. Are all keys open, which means you receive FF, you continue reading. If any key is not FF, then wait for key debounce. So if this key is pressed, you have to wait a few milliseconds. There's a debouncing, and then you read again for key pressed again. You continuously. So this is for one row, this is for the second row, and you continue for your check, and you can find which key is pressed and then continue a program according to that input from the user. So this is an application of 8285. Again, another application by using 8255 programmable output ports. So these are connected to data bus and other control pins, and some resistors are serially connected. So you use port A and port B of the programmable output control integrated circuit. Port A controls transistors. If any transistor, if any signal at here is high, then this corresponding transistor conducts, and it's connected to the one segment parallel to all 7 segment LEDs, and each segment's common signal is driven by PNP transistor. So if any signal at here is low, then corresponding transistor is conducting. If any signal at port A is high, then corresponding NPN transistor is conducting. So you can blink at least one LED by sending information, low signal to. Once again, if you want to turn any number at this 7 segment display, you send low signal to PNP, activate the LEDs, you activate certain information. For example, if you activate all transistors, all signals 8, then all segments will be on and you see 8. If you activate some of them, you see another number, and then when you increase this level to high, these will be all turned off. Then you can apply low signal and send another number here. You continuously see lots of the numbers and continue the rotation. If this rotation is fast enough, you see a, let's say, 8-digit number display on here. So by using 16 line, you can derive 8 digits, 8 by each 7 segment and 1 display. So you can derive 56 different LEDs by 16 lines, which is a saving. But nowadays, most people are using LCDs. People are not using 7 segment displays anymore. That much complexity is not required in today's microprocessors and controllers. So that's about it. I hope this will be helpful to understand your hard to understand topics in ELE 336.